colleagues and students who have to hear this talk a second time. Bruce is going to suffer again. But, and the students who came to the lecture I gave in KAIST. So unfortunately, I don't have new jokes, so I have to recycle the old ones. And also, I'll have collaborators on this work, and I'll mention them as I go along. So the idea is to take some small singular perturbations, which comes up, I think, in the first talk. People mentioned the work of Natalini. We came in as we arrived, and that's relaxation. And the first one will be a part of the talk will be about relaxation, and the second one is the case when relaxation usually means to have some dissipative mechanism that's driving the driving the system to the relaxed state, and the alternative to relaxation in dynamical systems is oscillations. So I'll talk about two problems, one with relaxation and the second one with oscillations. So first, let's talk about the relaxation problem. And it's the flocking problem, which our host, Sung-Gil Ha, introduced me to. And this is joint work with Sung-Gil and our Italian colleagues, I would say, who are at L'Aquila. But since L'Aquila is under some state of existence or non-existence, in the future they will return to L'Aquila. And this will appear in the Quarterly of Applied Math. And let me explain the idea. The equations are there, but it's better to understand the idea. So if you imagine that you have a bunch of birds flying around, and the birds eventually start going in flocks. And the question is how to model the flocking phenomena. And one way to do it is this Kuka-Smale model, which says it's F equals ma. So here's just defining the velocity. So each point xi is a point of the bird flying in 3 dimensions. So that's the velocity of the birds. And now this is, okay, the rate of change of the velocity, the acceleration of the birds, in fact, has a damping mechanism. This is a phenomenological model put together by Kuka and Smale. So there's a damping mechanism, and the question is, okay, what's the behavior of the damping mechanism? So that's not for the first issue, so let me now define terms. What do we mean by flocking? Flocking means that the velocities of all the birds will eventually approach some common velocity. That is, they'll all go to, the differences will go to 0. And also, the flock doesn't grow without bound. So in physical space, okay, the distance or diameter of the flock stays bounded. Okay, so that's the definition of flocking. So that's one model. Okay. Now, before I mention that, so we have for that model almost a complete theory of flocking due to Sung and Jung-Hwa Lu, which says that Kuka-Smale will yield flocking. Okay. Then as I read the literature, sitting around one summer, there's a whole bunch of papers by these guys who are Erdmann and Eberlinger in Germany, German physicists, okay? And they've written a whole bunch of papers on what they call swarms. Okay, so what's the swarming model? Well, in English, swarms, flocking, all the same. Okay, so in Germany they call it swarms, and Sung calls it flocking. Okay, so what's this German model? Well, the German model is a little different. Okay, that's really classical particles. So here's again the velocity defined by the rate of change of the position in space, and now this is just the usual dynamical system. So this would be Hamiltonian dynamics almost. So be the rate of change of a particle samples, okay, how this particle sees all other particles. So the birds are interacting by some potential, which is phi. And there's some damping mechanism, which means that the birds have wings, so they can slow down if they want to form the flock. So they have some way to put in a damping mechanism by putting out their wings. So here we were stuck. Okay? You have the, let's say, here's the group Smale, Sung, on one hand, who say flocking. And here's the Germans, on the other hand, who say particles. So you have two different models, same phenomena. Can't be. Okay. So one has to be connected to the other. So what's the idea that we put in our paper, which is very elementary, but it's a relaxation issue. Okay, so not everybody here is familiar with relaxation. So all we do is take the second equation in the German model, differentiate with respect to time. Couldn't do anything more simpler. So now now the acceleration is now a new independent variable, and there it is. New dependent variable, there it is. And now we just record the first derivative of the particle model, the second term in the particle model. Okay, so there's the forces, and now we just differentiated it. Okay, not a big deal. And what happens? Okay, well, formally, you let epsilon go to 0, then you get this equation, but that gives you a formula for Zi. If you plug Zi in there, that's Kuka-Smale. So Kuka-Smale, while originally written down by Smale and Kuka from City U in Hong Kong, is phenomenological. What it really is, it's not phenomenological. It's just particle mechanics, okay, that we can derive in a very elementary, but no one seems to notice it before, relaxation limit. So the relaxation limit, why can you take the relaxation limit? This is a classical theorem of Tikhonov in the Russian literature, though re-derived and generalized by hundreds of people, is because of the minus sign here, right? It has the right sign for relaxation because it's a dissipative, which was just related to the damping having the right sign. So in short run, what's the theorem? Oh, first the theorem. How do you prove that this one is flocking? Well, you take this one, so you combine relaxation with the results of Ha and Zheng Lu, and you get them together, and you'll get that because we knew flocking at the Kuka-Smale level from Sung's work, then we know flocking at the particle level by putting the two together with relaxation. So it's a combination of the two results. Okay? But what's, in my view, what's more fundamental, it turns out, I think the particles are fundamental, because you can derive, from the particles, you can derive Kuka-Smale. Okay, so I thought that's a nice result. So that illustrates one thing I wanted to talk about. So there I mentioned it. So classical Tikhonov yields particles, which yields Kuka-Smale, and Kuka-Smale yields the flocking result for the particle model. So we put everything together. And if you want an extra lecture on flocking, of course, ask our host, who's the expert. Okay, now second part of the talk. Okay, I said I'd talk about the reverse somehow of relaxation, which is oscillations. Okay, and that's often familiar to the people in conservation laws. Though here there's no conservation laws right away, so you have to give me a few minutes to get there. So this part 2 is called non-classical averaging, and the work has appeared with my co-conspirators in a couple of papers. So this one's already appeared in nonlinearity, and this one's going to appear, we hope. It's been submitted to Siam Journal of Numerical Analysis. So the articles are with my longtime collaborator Tzvi Artstein from the Weizmann Institute, Yanis Kevrakidis from Princeton, Idris Titi from part-time at Weizmann, part-time at UC Irvine, and in the second paper, Bill Gia, who hangs around in Princeton these days. And one of the things, as I remark always, is some people like to use Gear's method for solving ODEs. In this paper, we do even better. We don't have Gear's method, we just have Gear. And he's a smart guy, so it's good to have him helping us with the computations. So let me explain the problem. And I'll start off with ODEs, and we'll get to PDs before I'm finished. So here's the system of ODEs. So imagine we have a system of ODEs in n-dimensional space. And again, you'd think there's a relaxation mechanism. So here's the UDT. Here's a nonlinear function, f of u, rescaled by epsilon in the bottom. So this is, in itself would be a fast system. And then there's a slow part, g of u. And the question is, what happens as epsilon goes to 0? Now, usually in the fast-slow literature, which is tens of thousands of papers, okay, the research is usually to the write down a fast system and then separately a slow system. That's what we usually have in relaxation problems, and probably that's how the first lecture had fast and slow. But here there's no separation. Okay, you don't know a priori fast separated from slow is all mixed together there. So how to go about solving it? And the reason I thought this is a proper topic for this workshop is because the ideas are based on the kinetic theory of gases. Even though it's ODEs, we're thinking about, in the back of our minds is the Boltzmann equation. So if you want to think about it, this is the Boltzmann equation with some slow part there. Okay, so first we need to make it work. I'll start off with one. We need at least one, but then we need more, conserved quantities for the fast system. Well, you know, for the Boltzmann equation, you have mass, momentum, and energy. The first 0th moment, first moment, second moment. Okay? Those are conserved quantities. That's just the conservation laws. So we would expect those to occur. So we need, for OD, just a conserved invariant. So we need a Lyapunov function for the fast system, okay, that is conserved, doesn't change in time along the fast system. Well, just differentiating expected time. That's saying no more than the gradient of v dotted with f equals 0. Okay. So we call f a microscopic observer, a measurement, if you want. And if you want to think about it with respect to fluid mechanics, it could be thought of as the density or momentum or energy. Okay, so now what we want to think about now for the fast system, just the reverse, as I said, of relaxation. So in the usual relaxation story, as epsilon goes to 0, it's driving f to where f is identically equal to 0, and you reduce the order of the equation. But in this problem, no such luck. Okay, there is no damping mechanism here, and the solutions to this guy are oscillating around. Okay, and they don't have to be any preferred, but we're not making any assumptions. Okay, so it could be decaying, it could be part decaying and part oscillating. No assumptions. Okay, and I'll get to the only assumption in a minute. Okay, so our goal is to find out how v evolves, the Lyapunov function. So we differentiate, of course, with respect to t. This term is equal to 0 because the gradient of v dotted with f is assumed to be equal to 0 because it's conserved quantity for the fast part. And then this leftover part, gradient of v dotted with g. So if we put the first one down, I just rewrote it. So the change of v with respect to t is the gradient v dotted with a g. Okay. Now imagine, okay, we did an asymptotic expansion. This lecture isn't about asymptotic expansions. Asymptotic expansion is just a formalism, and what we get is a true theorem, okay, as opposed to the untrue theorems I prove. So this one's but imagine you wanted to know what's happening to the full system. Well, you could expand it in a asymptotic expansion, so to the leading order, because all the action, all the interesting stuff, okay, is in the fast part. If you expand it to leading order, all you see is the fast system, because the other part is slow. But this one, of course, you could rescale t, move the epsilon over inside the t. So, of course, this one could be rescaled to see that the solution to the fast system looks like a function of t over epsilon. Okay. Now, here's the only assumption. We assume the solutions to the fast system, either a function of t over epsilon or s, if s is t over epsilon, we assume the solutions to the fast system are bounded. So they don't go running off to infinity. Okay? So they're bounded in phase space. Okay, so now we get to the PDE part, or the ideas coming from PDE that people may be familiar with. Okay, so we have this fast system. Okay, this is the solution to the fast system, and I assumed it was bounded in phase space, so here I wrote it bounded in L infinity. So I know I can extract from that a weak star convergent subsequence. Okay, that part is easy. But how about functions of this guy? Well, functions of this guy, will they converge? Weak star. And the answer is, of course, in general, no. Just think about f of u equals u squared. If u converges to to a limit weakly, u squared is not likely to converge to its limit, whatever the limit squared is, weakly. That is, weak continuity is not to be inherited. And the reason is because that would imply weak continuity implied strong continuity, which is impossible, except for linear guys. And this is a nonlinear guy. So what's the weak limit of this f of u's? So if you have a continuous function, you want to know the weak limit. And the answer is you can represent the weak limit in terms of the representation in terms of a Young measure. So that just means you can, there's a probability measure that you can represent the weak limit by taking the, applying f to the measure and looking on it over the state space where the solutions lie, k. Okay, now this idea, of course, has been used in conservation laws, but of course was invented by my late colleague, distinguished colleague, L.C. Young from the University of Wisconsin, who was a smart guy. Okay, so let's apply that idea and see what we get. So let's go back. And so there I go back. So remember, I differentiated v with respect to t. The term with the f dropped out, and there was just this term, gradient of v dotted with g. So now, to leading order, it just looks like I could have plugged in the fast solution. Okay? So if I have the solution to the fast problem equals this guy, I can hardly resist integrating both sides and passing to the limit. So I integrate both sides, pass to the limit. So what do I see on the left-hand side? I see, again, v applied to the Young measure. This is just the initial data, which is fixed. And now we can pass the limiting process right through the integral. And it looks like I've now found an ODE for v against its Young measure. And that tells me how the measurements, say the density, momentum, or energy, propagate in space because of the effect of the slope part, g. Okay, so you can write it this way. If I call this guy v0 of t, it looks even a little nicer. Okay, it's not quite an ODE because the initial data is buried in here because that determined the Young measure. But as a way, given the past, you can compute the future. Okay, so it's an evolution. Okay, so now what does it lead to? And I'm embarrassed to say, because I've never written a paper in computations, well, maybe one. Once every 20 years I write something with computations. Okay. So, but this is really a very nice way to compute. So if you want to know, think about it. You have a system as this fast part and then a slow part. And you want to see the effect of the slow part on the system. So you want to wait a very long time. Eventually the slow part has an effect. Okay? And you want to see what's the effect of the slow part. Well, one way is just to compute forever and that resolve the fine scale epsilon, and that'll do it. But you don't have to. And that's the beauty of the whole thing. So let me explain the algorithm slowly. Okay. So what does it say? We have to compute. Let's go back an instant replay, because let's make it clear. I wish I had. Let's look at the algorithm is all buried in this box. Okay. So to know how to advance the measurement, okay, I have to compute this integral. So what do I need to know? I need to know the Young measure. So first I need to know the Young measure. Once I know the Young measure, I know V, I know G. So then I can perform this integration numerically, and now I know V at the future time. And then I can continue this process. So first I have to compute the Young measure. So we do that. So how do you compute the Young measure? It sounds worse than it is. In fact, it's very easy. Okay, so you take your system, the fast system, and you run it for a little bit of time. Well, since it's fast, it's zipping around like that, oscillating around, having a good time. Okay, then you can sample it, okay, and you can compute V just according to that rule at time t1. So you run it out a little bit of small time, okay, sample, and according to that integral formula, you can integrate V compute V at time t1. Now you do exactly the same thing, repeat the process, but now run it out to time t2. So 1 second, and then you run out for 2 seconds. Okay, so now I have V at time t1 and V at time t2. So I've sampled, computed a Young measure just by sampling a bunch of points, and I do the same thing, and I have V at time t2. Okay, now I tell the story that when in the olden days, like last year, when I taught undergraduates, but now I don't teach undergraduates, okay, we always tell them an introductory course to ODE, don't use Euler's method for solving ODEs. It's terrible. Use something better like Runge-Kutta or working with Bill Gear's method. But it turns out Gear uses Euler's method for this problem. You could use Runge-Kutta, but that's not worth it. Okay. So what do? You do the dumbest thing in the world, which is an idea of Yanis Kevrakidis, who's really made a big business on this. So it's called projective integration. Okay? So it's embarrassingly simple. Okay? You have V at this point, you have V at that point. Connect the points by a chord. That gives you, usually in ODEs, can I write it here? If you had an ODE for V of something like that, how would we tell the students to do it? We'd say, oh, okay, you would write, so you'd have to divided by H, right, and then something over here. So we tell the student, given the vector field, you can find out how to advance the V. This is just the reverse. Okay, given 2 points of the V, we find the V dt, so we know its slope. If we know its slope, I know an approximation to the f. So instead of given f, find the slope, we do find the slope given f, gives f. So it's just the reverse. So once I have the slope, okay, I project it way out and then start the process all over again. If I start the process all over again, what did I need? Well, I needed some way to compute those fast motions. So I have to find a bunch of data which is consistent with the V's I get by this projection. That's called, in the language of multiscale, the lifting step. So you have to, again, find a new bunch of so-called microscopic data and then repeat the process. Okay. What's the important thing from the point of view of numerics? Okay. The small scale epsilon is never resolved. Epsilon is lost from the problem. Even though it's a fast, slow system, there is no epsilon, which is fantastic. Okay. Yeah.
You have more than 2 scales?
No, this is only one. So it's epsilon. It's only one small parameter.
Right, but I assume you have an epsilon and an epsilon square or something. 3 scales. Like
3 scales. Well, I haven't thought about it, so.
But I'm sure Kevrakidis has.
I don't know. Not on this one. Actually, so Gear had worked with I think I'm not aware, Linda Petzold, and they were talking clouds and stuff to try to, and they didn't realize, okay, the power of the Young measure. You didn't need this abstract, somehow pseudo-numerical mysticism. Okay, the answer is all hidden in the Young measures, which we know about from conservation laws. So, but it's not in their lingo. So our job from the math point of view was to introduce the notion of the Young measure. That really what you want to do when you're running around here is, it's interesting that it's a numerical analysis, but it's a probabilistic approach, which is good enough, because that's what the Young measure is. It's a probability measure. So we've introduced, even though it's a deterministic process, we've introduced probabilistic notions. Okay, let's get down to business. So here's an application. Well, I think I'm on schedule. Okay, so here's the application. Of course, there's others. Now I can mention names of people in the audience where it might work. Okay, so in a second. So the application we have in mind here, because it was easy somehow, is this system of ODEs, okay, which if that bothers you, so it's quadratic there and linear there. So this looks like Laplacian. This is a quadratic term, okay? And we put on periodic boundary conditions, okay, because we want oscillations, okay? So this is if you took the limits and you'd expanded in Taylor series, this is the upper one is the discrete version of the KdV type equation with the Burgers term. So it has a viscous term there. So it's a KdV type Burgers, but it's not the real KdV because the U sits outside times the U triple X. So it's fully nonlinear there. Okay. So it has, but the advantage of it is that the ODE is nice. Okay. So this idea, of course, is not new to us. This was the system written down by Lax and Goodman when analyzing oscillations for KdV. Okay, just to remind you, if you wanted to see it, so if you took this discrete version, this would be the F, and the G would just look like the Laplacian, okay? Finite difference approximation to the Laplacian, second derivative with respect to x. So that's the system of ODEs. And why did I like that system? And the answer is because, as I know from the work of Lax and Goodman, if I take the u's and now call them a squares, I can rewrite the fast part without the Laplacian in this form, but that system admits a Lax pair. So it's very nice. So you have lots of conserved guys. That means lots of observers. Okay. Lots of conserved guys. The more V's you have, the more information you have. So there's the Lax pair. So this is a matrix L and capital matrix B, such that this system can be represented in this Lax pair. Okay, so what's so great about Lax pairs? And how do you find them? Well, I'll answer the second question first. Okay. How do you find Lax pairs? And the answer is it doesn't hurt to be Lax. So Lax knows how, and it's somehow magic to me how Lax finds these things. But here it is. So there's an example in the case L equal to n equal to 6. What's so great about them? And the answer is, well, if you differentiate any power of L, it always turns out to be the commutator B LP. So it's B times LP minus LP times B. What's so great about that? Well, AB, of course, doesn't equal BA if A and B are matrices, but their traces are equal. If their traces are equal, then the difference of, when you take traces here, then the right-hand side is 0. So the traces of L to the P are always invariants. So we can produce a whole bunch, in this example, of non-trivial invariants, so it tells us how to compute. Okay, I don't think I'll talk about that one. It's a connection with Hamiltonian systems, but I don't want to use up all of the time. So let's get to the essence. So let's show some numerics, and then I'll make a couple of comments. So for example, what does the fast problem look like? And we plot it out here. So there you see it's running around on a torus. And of course, I can't. This is the case n equal to 6. I can't show you a 6-dimensional torus, but I can show you what it looks like by a projection into three of the 6 dimensions. And you see the fast system is running around having a great time. And if I plotted just some time snapshot of what the fast system is doing, say this is the first lax invariant, okay? No, the first component, sorry, of the U's as time evolves, and you see it's oscillating again, having a great time. So highly oscillatory. Okay, let's skip that one. And now let me get to the essence and then a few remarks. So here I think this is a good picture to stop the view graphs with. So let's get to the story. So there's 2 ways to solve this fast-slow system. One is to resolve all the steps, just plug in your favorite code, Runga, cutter, or whatever, and grind it out. The other way is to take this little snapshot, little micros, run the fast system a little way, then project, and then redo it all over again. So here I have 3 pictures of the different invariants, okay, to see how they evolve on a long time. Okay. Now the question is, what am I showing you? The system grinding it out, or the system by our method? And the answer is we've plotted one on top of the other. Okay. That is, to the eye, you cannot tell the difference. So this method of taking these big jumps, as far as the eye can see, works perfectly. Okay. And there it is. So now to approximate how much better, it depends. The smaller the epsilon, the better our method. Okay. So I think we said something in here. So for epsilon about 1/10, whatever that means in this scaling, ours is 40 times faster. So the smaller the scale, the epsilon, the faster the method. So now, before I stop, I'll mention 2 other possible applications that come to mind. Okay. One is I heard Eitan talk, Tadmor talk in Minneapolis, but then Philippe reminded me he's also worked it. So if it's some of the entropy conserving schemes. So that would be the fast one. So if you had a fast entropy conserving scheme and you want to now put a slow term on it, okay, which is going to ruin the entropy conservation, you could still use the entropy conserving scheme. Just run it a little way and then average it against the non-conservative part, and it should work just fine. The other one might be nonlinear Schrodinger, which there's some, again, if you take nonlinear Schrodinger, you could have a fast part, maybe from the classical linear Schrodinger, and then put on a slow part, and again, you can average the slow part against the fast part and really accelerate the computation. So those are, of course, that's unfair to wake up the audience, but anyways. But a good place to stop. So I thank everybody.